so question 2, ozone, dinitrogen monoxide, CFC, sulfur hexafluoride, are all greenhouse gases. Only part of this is important. Draw one valid Lewis structure for each molecule of the greenhouse gases listed. Okay, so you've got ozone, you've got sulfur hexafluoride. Ozone, we've studied it, we've studied the fact it's got resonance structures, so there are multiple ways that you can draw this. This is one of them. If you're not sure on how to draw Lewis structures, this isn't a time that I'm going to go into that. Can I ask you to check out the MSJ Chem tutorials on that? And here we've got the oxygen with 2 lone pairs and this oxygen with 3 lone pairs. One of the most common mistakes is to miss out these electrons here, or to have 3 lots of electrons here and 2 here. So it's just making sure that your numbers add up. And then sulfur hexafluoride, remembering that sulfur obeys the expansion of the octet rule. So you've got sulfur at the centre, you've got 6 fluorines coming off it. And the most common mistake here is to draw the sulfur and the fluorines and to forget to add in the electrons that belong to the fluorines. So you have to make sure that you've added in all of those. Doesn't matter if you use the dot method or if you use the bar method, as long as you stick to whichever method you've chosen to use. Okay, next question. So whenever you're doing any questions on shapes, you always need to consider a few things. The rules are, look at how many electron bonding regions are present, so bonded or unbonded, to get your base geometry, and then we look at the molecular geometry afterwards. So deduce the name of the electron domain geometry and molecular geometry for each molecule listed below. Ozone and sulfur hexafluoride, you've just drawn them on the previous page. So ozone, question number 1, how many bonding regions does it have? Now if we look back at the molecule, it's got 3. So that ozone at the centre, that oxygen at the centre of the ozone, has got a double bond on the left, a single bond on the right, and a lone pair at the top. That's 3 areas where it can bond, so 3 bonding regions. So, if it's got 3 bonding regions, it's trigonal planar. How do you know that? You know it because you know it. It's revision. That's something that you just have to know. It's a fact. The electron domain geometry, so this is based on the regions that it has. Your molecular geometry takes into consideration how many lone pairs you have. So because one of those 3 regions is a lone pair, it's not bonded, instead of having that trigonal planar shape with your oxygen at the centre, your double bond, your single bond and another bond, because this one here is a lone pair, what you actually see is a bent shape. So bent or V-shaped would be your molecular geometry for your ozone. Sulfur hexafluoride, it's got 6 bonding regions, so octahedral. All of these bonding regions are bonded, there are no lone pairs, so it remains octahedral. There's no change, there's no difference there. Next question, identify which molecule, given in part A, has an extended octet. So extended octet, expansion of the octet, doesn't obey the octet rule. It's asking for the molecule. Quite a few of you wrote sulfur. It's not sulfur, sulfur's an atom. Sulfur is the atom that has the extended octet, but it's asking you for the molecule. So the molecule is sulfur hexafluoride, so you have to bear that in mind. State the bond angles for each of the species in part A. So we've got ozone, sulfur hexafluoride. You've looked at your base geometries. This is facts. Facts knowledge A01. Ozone, 120 degrees, because the base geometry is trigonal planar, but because there is one lone pair, lone pairs repair more than bonding pairs do, so 120 degrees is your base geometry angle, and then because of the lone pair you've reduced that by roughly 2.5 degrees, so somewhere in the region of 117.5, 118 would get you the mark there. 120 you would not get the mark for, okay, because it specifically is no longer 120 because you have got that lone pair. The point here is that you're indicating that you understand that the lone pair has that extra repulsion. Sulfur hexafluoride, the base geometry and the molecular geometry are the same. There is no lone pair, there are no alterations to the bond angle, so it remains at 90 degrees. Draw the resonance structures for ozone and lone pairs should be drawn. Okay, again, as I mentioned with the previous slide, problems were to do with just not balancing out your electrons, not counting them up. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Just go back and check that all of it matches. And these are the two structures that you would need. You don't have to include the actual hybrid resonance structure, the one that we did where you've got the semicircle in the middle, because that is the hybrid, if you like, the mixture of the two that we use as an indication. Okay. Formal charge I'll do separately.